In this video, we're going to continue with our discussion on line integrals. So to look at this, so far, we have integrated with respect to arc length, so our ds, right, our s function, which ds is integrating with respect to our arc length, s. So what if we don't want to do that? What if we want to integrate with respect to x, y, or z? So we may want to integrate with respect to x, y, or z. Okay, we'll see in a little bit why we might want to do that, but for now let's just assume we do. And it turns out that the integral over a curve C of f of x, y, and z dx is actually the integral from a to b, so we're going to rephrase everything in terms of t, of f of x of t, so x is some function of t, y is some function of t, z is some function of t, and our dx is really just x prime of t dt here. So again, we'll see a little later on why this might be useful, but for now, this is how we're going to calculate that. We actually get something very similar if we want to integrate with respect to y or z. And again, how do we do this? Well, we have some curve C that we parameterize that curve C, parameterize the x, y, and z in terms of functions of t, so in terms of t. And then we go ahead and we plug in our x, y, and z in terms of t into our function of f, and the dx becomes x prime dt. Okay. Now, furthermore, it turns out that sometimes we may want to integrate with respect to x and y at the same time. So, and possibly z as well, but for this example, we'll just do this over a plane curve, so we only have x and y. In this case, we shorten the notation to and we'll write out what the full notation is, and then I'll show you what the shorter notation is, but the full notation is the integral of c over c of some function of x and y dx plus some integral over that same curve C of some function q of x, y dy. And if we are doing something like this, where again x and y are in terms, will be parameterized in terms of t, so we'll have some function x of t, some function y of t, dx will become x prime dt, and dy is going to become y prime dt. We can often shorten this notation to just over the same curve C, we have p dx plus q dy. So often we'll write it like this, and so we'll see that come up a little bit later as well. Before we get into all of that though, let's just do an example where we use something like this. So our example here is going to be find the integral over the curve C of x squared dx plus y squared dy, where C consists of the arc of the circle x squared plus y squared is equal to 4 from 2, 0 to 0, 2, followed by the line segment from 0, 2 to 4, 3. So before we do anything, let's draw that picture out. One, two, 1, 2, 4, 3. So we start on the part of the circle, the quarter of the circle, from 2, 0 to 0, 2. And then we have a line segment from 0, 2 to 4, 3. So we have two curves here. We're going to call this C1 and C2. And we want to integrate over both of those curves. So for C1, what is our parametrization, right? We have to have a parametrization for each of these curves. For C1, x is 2 cosine of t, and y is 2 sine of t, right? We're on a circle of radius 2 here. So what is x? X is r cosine of t. Y is r sine of t. R is 2. So we go ahead and write that out. And this is, of course, true as t ranges between 0 and pi over 2. All right. So let's go ahead and calculate the integral over the curve C of x squared dx plus y squared dy. Well, this integral is x squared dx. Okay, so this is the integral from 0 to pi over 2 of x squared. So that is 2 cosine of t quantity squared times dx here, which is x prime dt. What is the derivative of x? Well, that is negative 2 sine of t dt. And of course, we add this to this. Y squared dy. Y squared is 2 sine of t squared times dy is y prime. Oh, sorry. It's running off the page a bit. Dy is y prime dt. What is y prime? Well, that is 2 cosine of t dt. Okay, so this is y prime of t dt. This right here was x prime of t dt. Now to actually finish this up, I'm going to leave that for y'all, but to finish this up, notice that this right here is a u sub with u equal to cosine of t, and the derivative of that is negative sine. So you can just integrate this piece with a u sub, and you can integrate this piece with a u sub as well, but u is now sine of t, and du is cosine of t. Okay, so I'll leave y'all to do that. But I want to go ahead and write out what we would get for C2 for the curve here, part 2 of the curve. Well, for this, we get x is equal to, this is a linear equation here. So x is a linear equation as well. For linear equations, we want to use t ranging from 0 to 1. So at t equal to 0, what is x? X is 0. And it increases to 4 as t ranges from 0 to 1. So that is the linear function for t plus 0. Because our slope is 4 and our y-intercept, or really x-intercept in a sense, is 0 here. We also need a parametrization of y. Y starts at 2 and it goes to 3. So that is t plus 2, right? Starts at 2, and as t increases by 1, it goes to 3, so that tells us our slope is 1, because we moved over 1 and we went up by 1. All right. And again, how would we write that out? Well, for this, we would get the curve C of x squared dx plus y squared dy is equal to the integral from 0 to 1 of x squared, that is 4t squared, times dx, which is x prime of t dt. What is x prime? Well, that is 4, and then dt. Plus y squared. Y squared is t plus 2 squared, y prime, which is 1, dt. And we can integrate each of these over the integral, or over the bounds 0 to 1. And of course, our final solution to all of this is the sum of this integral plus this integral. But I'll leave that to y'all to finish up. There's one more thing in this video that I want to look at. And that is, or a few things, a couple of things really. That is to first note that if we have a vector field F here, which is, we can write as Pi plus Qj, plus Rk, then the integral over some curve C of F dotted with dr is equal to the integral over the curve C of F dot R prime of t dt, which is the integral over the curve C of the dot product of the vector PQR dotted with x prime of t, y prime of t, z prime of t, dt. But what is that? Well, that is the integral over the curve C of exactly p x prime plus q y prime plus r z prime dt, which is exactly the integral over the curve C of p dx plus q dy plus r dz. So, earlier when we were writing out this, and we thought maybe this is strange that we integrate with respect to dx and then integrate with respect to y and integrate with respect to z here, and try to do all that all at the same time. Well, actually, that's kind of natural, because that's what we end up doing if we write out f dot dr, the integral of f dot dr, which is our line integral over a vector field. So we actually end up getting exactly that, what we had just kind of worked on and practiced. All right, that's very neat. Let's go ahead and say one last thing in this video, right? And so, given some parametrization, x equal to x of t, y is equal to y of t, and z is equal to z of t. So x, y, and z are just written as in terms of t. And oops, sorry, I'm actually going to do this with a planar curve, so let's ignore z there. And we can write this over some interval a to b. So t ranges from a to b. Well, if we do that, this determines an orientation, or in other words, a direction of the curve C. Okay? Where the positive direction is given by increasing values of t. All right. So, for example, if I draw a picture here, so some curve C, and we go from A to B, then this implies that we are moving in this direction here. If I draw that same curve C, but we want to move the other direction over that curve C, so from B to A, this is really the negative of the curve C. And in fact, if we wanted to write this out, if we are doing the integral in the negative direction of f of x, y, dx, and we're integrating with respect to x, this is the negative of the integral in the positive direction over c of f of x, y, dx. So if we integrate with respect to x, and we change our bounds, so instead of going from a to b, we go from b to a, that is the negative of going from a to b. The same thing will happen if we integrate with respect to y. We actually get negative the integral over c of f of xy dy. But interestingly enough, if we integrate with respect to arc length, that does not happen. So if we integrate with respect to arc length, this is just the integral from c over c of f of xy ds. So we don't put a negative symbol out in front. We are not taking the negative of the integral. Turns out these two integrals will be the same if we integrate with respect to s. Okay? And that will end our video.